Hello, everybody, and today we will look at neutrinos. So, I've prepared some slides, and while getting this content together and while making this video, so I knew something about neutrinos already, but it's been quite enjoyable for me putting this together because I got to know even more interesting things about neutrinos and how it fits into the I was going to say big picture, but it really is one of the tiniest particles. So, yeah, but how it fits into the big picture. So, so there's a lot of stuff around it, and there have been a number of Nobel prizes around the neutrino, and really considering that it's so tiny, it does fall under the realm of it has to be addressed quantum mechanically, and because also it is found in cosmic rays and in cosmic processes. So it travels at high speeds, and in that sense, also we have to look at it. So it does for treatment for neutrinos does come under quantum mechanics and relativity, and so what I'm trying to say basically, it's a large subject, it's a large topic, and so we'll just go through these slides and. For further information, you can Google yourself, pause where you want to see more, or get back to me with questions. And so I'll just browse through this material. So, what is a neutrino?
We know the neutrino.
So, now you know what a neutrino is. But, okay, so let's look at it in the context of matter. So, this is matter here shown as comprising of atoms. And when we look at one atom, we can see that it comprises of a nucleus, which in turn is made up of protons and neutrons, and there are electrons kind of in a cloud rotating around the nucleus is the picture that we're kind of more familiar with. And over here what this goes on to show is that each neutron and proton are in turn made up of, or each nucleon, that is either proton or neutron, is made up of three quarks. And we've pulled out this neutrino over here. So given this structure of matter where they've shown there are neutrinos over here, let's also take a look at what Wikipedia has to say, for example, about what neutrinos are. This is what Wikipedia has to say. A neutrino is a fermion, and a fermion so this is what Wikipedia has to say. A neutrino is a fermion, and a fermion is an elementary particle with spin of 1/2 that interacts only via the weak subatomic force and gravity. And it is so named because it is electrically neutral and because its rest mass is so small that it was long thought to be zero. So let's look at some points of this before we go further. Maybe it will make sense, maybe not, but we'll just quickly look at it. So, okay, there is a fermion, which is an elementary particle. So we'll also look at elementary particles shortly. So an elementary particle is something that has no substructure. So these are elementary particles with spin of 1/2, and it interacts only via these two forces, the weak force and gravity. So these are two of the four fundamental forces. The fundamental forces are the strong nuclear force, the weak force, and electromagnetic force, and gravity. So the neutrino interacts only via these two forces. Also, it's electrically neutral, unlike the proton or the electron. So it is neutral. and its mass is so small that it was long thought to be zero. In fact, um, uh, in a lot of publications till recently, they used to kind of say that maybe the neutrino has no mass, but the 2015 Nobel Prize was awarded for for neutrino oscillations for the discovery. So the Nobel Prize of 2015 was awarded to Takaki Kajita, Arthur McDonald, for the discovery of neutrino oscillations, which shows that they have mass. So it's accepted now that neutrinos have mass. But before we jump to whether they have mass or not, let's see about. So they were first postulated by the famous scientist Pauli, and he was the one who postulated neutrinos. And we'll also take a quick look at why we thought there would be neutrinos and how they were subsequently identified. So let's take a quick look at where neutrinos are found. So over here, I'd just like to point out that one of the places they're found is in radioactivity. So as we know, radioactive processes have alpha, beta, and gamma rays. So in the gamma decay of atomic nuclear hadrons, we get to see neutrinos. Now, if we see the Wikipedia page for beta decay, for example, so that's a beta decay. Beta decay is of two types: the positive beta decay and the negative beta decay. In the positive beta decay, it gives out a positron. In the negative, it gives out an electron. So we can see right here. So this would be a negative beta decay, where a neutron converts to a proton via an emission of an electron and an anti-electron neutrino. Or so if you see now, considering that this is a beta decay, where the neutron gets converted to a proton, and this, in fact, will result in a change in the atomic number by +1. So you can see this page has got a whole section on neutrinos, beta decay. It's got a whole section on neutrinos, and so there were a number of problems when they were studying beta decay. They noticed that while the alpha and the gamma particles, they have a narrow energy distribution. However, that was not the case for the beta particles. And also, so that was one problem, that it didn't have a narrow energy distribution. And the second problem was that it there was no conservation of angular momentum. So you can see how they found out that by measuring this. So basically, every angular momentum for small particles was that the spin was not conserved. And based on this, Wolfgang Pauli attempted to resolve the beta decay energy conundrum by suggesting that in addition to electrons and protons, atomic nuclei also contained an extremely light neutral particle, which he called the neutrino. So this further was renamed to the neutrino based on what he was looking for. So the point I was trying to make here is that because of conservation laws or the conservation property, so in case of the beta decay, they noticed that there was no conservation of energy, momentum, angular momentum, and that is why Pauli postulated neutrino. So if that was too much, that was, well, if you want to kind of keep it in the back of your mind for now, and let's carry on. So neutrinos are very tiny particles, and we saw that that was one reason for why. they started looking for it. And here is a picture where they're showing how a neutron. That was the same thing we saw in Wikipedia. It's now converting. So the blue is the neutron and the red is the proton. So now it's slowly turning into a proton by emitting an electron and a electron antineutrino. So in a radioactive process. And so this is what this slide actually is trying to show, how by study of the beta rays in radioactivity, Pauli postulated a neutrino, and this theorized particle was found by Rhines and Cohen in 1956. So all of these people have won Nobel Prizes. So this goes on to show how each nucleon is made up of quarks. So now when we say that, okay, this is a good part to see that now we say one element, right, is made up of atoms. And the atomic number is the amount of protons that are there in this nucleus. But due to nuclear processes, when there is a change in the atomic number, so we say there is a change in the element. Okay, we say one element has changed into the other, it's transmuted into another. But at this point of time, now we know that it is because the nucleus, which is comprising of protons and neutrons, there is a change from a proton to a neutron. But now that we know the protons and neutrons in turn are made up of quarks, so actually it's a change. So there are three kinds of quarks, which we won't go into now. And although there is a slide further on. So for example, there are up quarks and down quarks. So when an up quark changes to a down quark, that is when a neutrino are emitted, and there is a change in the element. So we'll have a look at that further. See, this is the slide. So a neutron is made up of one up quark and two down quarks, and a proton is made up of two up quarks and a down quark. When so now we know that a neutron turns into a proton with emission of a neutrino, but actually it is a down quark changing into an up quark when we look at it at a more granular level.
So Peter Stillwell is asking the question about, do neutrinos have mass? Question about, do neutrinos have mass? When neutrinos were first discovered, they were discovered because they carried away energy and momentum from nuclear reactions, and we couldn't explain them unless we could imagine that these particles would exist. Everything we could tell at the time was that neutrinos had no mass. They traveled at the speed of light, or very nearly. But then, in recent times, we've seen evidence that they do have mass. It's only very small. So the way that we found out was, number one, we know that the sun makes neutrinos, and we were not getting the right number of neutrinos here on Earth in our detectors. So we had to imagine that the neutrinos were turning into something else on the way. So it seems to be true. The neutrinos that are manufactured in the sun by nuclear reactions are turning into a different kind of neutrino before they get here. And so that's why we couldn't see them all. Similar things now have been observed with neutrinos that we manufacture in nuclear reactors. And so it seems to be true. Neutrinos do have mass. It's very small, but it can be measured a little bit. And this is a very difficult measurement, but we're pretty sure neutrinos have mass.
Okay, so the takeaway from that is that neutrinos do have mass. And the thing that he was referring to about changing from one kind to another, so we'll have a look at that. And that is also what was when we looked at earlier the 2015 Nobel Prize, the oscillations. That's what he was talking about, when changing from one type to another. So what are the origins of neutrinos? So we've already seen in radioactivity, which is a nuclear process. So we've seen neutrinos come out from nuclear processes. Radioactivity is an example of a nuclear process. And as he mentioned, our sun, which burns, in a manner of speaking, we say it burns hydrogen to create helium and heat and light radiation is emitted in the process. So let's take a look at that. So it's the reactions that we know are that four atoms of hydrogen combine together in the sun to form an atom of helium. So hydrogen is just a proton, and helium 4 with an atomic number of 2 is 2 protons and 2 neutrons. So as you can see, 2 of these protons have converted to neutrons, and all these have combined to form one nucleus of helium under the high temperature and pressure conditions of the sun. And in the process of hydrogen combining to form helium, a lot of energy is given out that reaches us as light, and neutrinos are also given out. So that is one way of saying it, but in fact, it has been found to be a series of processes. So the white balls here, the red balls here are protons. So this is the chart, and the gray balls are neutrons. These are positrons. So two protons or two hydrogen atoms come together to come form one neutron and one proton, which is still hydrogen. But in the high pressure and temperature conditions of the sun, I'm not sure whether giving it names like hydrogen or because I believe they all stripped of the electrons. And but let's go according to this chart is that two protons come together to form a neutron and a proton. Now they are one unit with the emission of a positron and a neutrino. And then again it combines with another proton, which is another hydrogen, and forms this thing over here, which is helium 3 actually. And this is also helium 3. And these two come together with the emission of two protons to form one helium atom. So actually, if you'll see, there is 1, 2, 3, 1, 2, 3. So there were 6 protons come together to give this helium atom and 2 protons. And in the process, there are neutrinos given out over here, 1 and 2. And the gamma rays are the energy. So this is the process of the sun. So this is the light that we get from the sun. And now there are billions and trillions of these protons fusing together in the sun to give us the energy that we get all these millions of kilometers away through space. And what happens to the neutrinos then? So we get the light. So this is what happens. Billions, so actually it's 100 trillion. Somebody's come up with this number, which must be correct. So trillions of these neutrinos pass through our body. Now, we've seen that for a long time people thought that maybe it had no mass. That's like light, like photons. But now we're saying it has tiny mass. So it's really tiny. It's tiny even compared to a neutron and a proton. And definitely it's subatomic compared to it is subatomic, it's subatomic particle, but it's really much smaller even than an atom, and it's very tiny, it's electrically neutral, and it just passes through us. So even while you are watching this and I'm making this video, trillions of neutrinos are passing through us. So, wonders of the universe. So here are some equations. So we've seen two sources of neutrinos, that is radioactivity and fusion in the sun. And if you remember, we saw in Wikipedia, or even the gentleman who spoke in the video, he said that you can see them in particle accelerators, and the largest one is CERN. So we've written there as well. And here we have a chart on the standard model. So I guess it's a new term, standard model. So there is a standard model of particle physics, the particles that we know exist and we study, and parent, and it's said to be the most perfect, most complete model in place right now. So this is a model of the elementary particles, those particles which are not known to have any substructure. So as we saw that, two up quarks and one down quark make a proton, or one up quark and two down quarks make a neutron, and so on. And these are the electrons. So these are the six quarks, and they sit in three families: one, two, three. And similarly, these are the leptons. As we saw in the definition when we were looking at neutrinos, we saw they are leptons with a spin of one half. They were fermions. So we have electrons and we have electron neutrino, muons and muon neutrino. So again in three families, one, two, three. So these are quarks, these are leptons, and these are gauge bosons, or also called the force carriers. So this is the carrier for the strong nuclear force. This is for the electromagnetic force, and Z and W bosons are for the weak nuclear force. And for gravity, gravitons are postulated, but they have not been identified yet. And this is the very famous Higgs boson. So these 17, 17 particles are the elementary particles of the standard model. So this is another diagram showing the same thing from the earlier one. There are three families. There are quarks, there are leptons, and these are the force particles. They haven't shown the Higgs boson here because it's not a force particle, but yeah. Four. So three families of particles, four fundamental forces, carriers of the forces. Very nice. These are some examples of weak interactions, pair creation, annihilation. These are Feynman diagrams named after the very famous physicist Richard Feynman. He came up with showing particle processes in this manner. For example, this one means an electron can decompose into an electron neutrino and a W minus boson, and so on. We've seen this already, neutron beta decay. So this is how it could be depicted in a Feynman diagram. And roughly we have seen there are three kinds of neutrinos: the muon neutrino, the electron neutrino, the tau neutrino, and the muon neutrino. This is a very interesting section. Now, there are trillions of neutrinos passing through me, and they are so tiny, they're electrically neutral. How can we detect neutrinos? So this is the Super Kamiokande observatory in Japan. So you can Google it. And there is no human here, but I believe it's underground in a mine, and this would be the entrance. So these are the detectors inside it, and I think they work on the Cherenkov principle. And you can see that these are the people over here. So they've built this huge setup to detect these tiny particles. And you could read more about it, or we'll make another video another time about how there are a few thousand particles detected over a long period of time, perhaps a year, and how sensitive the equipment is. And it's just mind-boggling that. And it also shows, like, since we've seen that how by first principles of conservation, that a neutrino was postulated and then identified. And you see there are all these sources and there are oscillations between them. And but really, this is the technology behind it, where there are these very sensitive detectors, thousands of them, trying to catch these tiny particles. So detection via Cherenkov light emitted by particles moving faster than light. And also neutrinos from cosmic rays come from decay of pions. And this is the solar neutrinos, which are found in, which are trying to be observed in the Sudbury Neutrino Observatory in Canada. You can see there's a man there, so you can get the whole scale of it. That is, so when the neutrinos pass through here, when they come in here, they will interact and then they can be. So as you can see for the Super Kamiokande, so as you can see for the Super Kamiokande observatory, it's a tank, 16-meter in height and about 60-meter in width, and it contains 3,000 metric tons of pure water and about 1,000 photomultiplier tubes attached to its inner surface. And, so it observes solar neutrinos, and also it observed neutrinos from a supernova which was observed in the large Magellanic Cloud, which is a satellite galaxy of the Milky Way. Each each of these roughly 6,600 photomultipliers, each costs about $3,000. So solar neutrino observations were observed in both the Super Kamiokande and in the Sudbury Neutrino Observatory. And there are a number of other observatories, like an underwater one, and in the South Pole. India is also coming up with a neutrino observatory, but in Tamil Nadu. And the site is in Tamil Nadu. So the Indian Neutrino Observatory. So the Indian Neutrino Observatory is planned inside a hill, and the access tunnel is about a meter long. So you can Google about this and read more about it, and also see why these observatories for neutrinos are built in old mines or inside hills. So it will be interesting to see why they do that. That's all we have for neutrinos, and I know it was a lot of stuff, but really, I hope you got an idea what neutrinos are and what people are trying to find and why it's important. And it's very interesting and exciting, and there's still a long way to go with it. And I know there's a lot of new stuff we've talked about today, but you can Google about it, or talk with your friends or get back to me. And thank you for watching.